Okay, 9.1, we're talking about antiderivatives. And as I just mentioned in the intro here, up to this point, we've been talking about derivatives of functions. Now we're going to be pivoting towards integral calculus, and we're going to be talking about something very important called antiderivatives. So you could probably guess the term antiderivatives is the opposite of derivatives, which it kind of is. It's actually, you think about if you're given a function and you're asked to find the derivative, we know how to do that. We've learned a lot of skills on how to find derivative and what a derivative means. Well, what if we were asked to find the original function, or the parent function, let's say, that the derivative came from? You ever thought about that? Well, we know all the rules going forward. Now we're going to start to learn the rules in coming backward. Okay? So we need to talk about the parent function, or the 1 year I called it the mother function. Yes, we're gonna try and figure out that mother function. We're gonna get to it. Yeah, I think mother function is on the tile here somewhere in my room. So yeah, don't overuse that term though. It's you get in trouble. All right. So let's take a look. If you remember graphing derivatives. You may or may not. It was pretty quick, it seemed. But graphing derivatives is what we would do is we'd start with a function, and we'd take a look at, what's the slope of the tangent line at a certain point, and then whatever that slope was, we would plot that on a separate graph, and we would end up plotting the derivative function. Well, guess what we're going to do today? We're going to take a look at a derivative function, and we're now going to go backwards, and we're going to plot the function that it came from. Okay, so how might we? I know what? How might we do this? Okay, so this is where we're going to start, and I want you, if you're you're copying this down, just make 2 coordinate planes there, and then sketch approximately, a graph that looks like this. Okay, just approximately. Yours might look just slightly different than mine, but this graph on the below, okay, we always did the function and then we graphed the derivative function below that. So I'm just going to keep them in the same sort of order. So if we start with the derivative function, what this means is this. Okay. So we start down here. The value of this derivative function here is -2. You see, this point right here. What that means is the slope of the tangent line of the original function was -2. So I'm going to pick a spot, a random spot, and I'm going to make a little tangent line that has a slope of about -2. So I'm going to draw a corresponding, right above this, I'm going to draw a tangent line that has a slope of about -2. Now, I don't know if that's exactly -2. It could be a little steep. Let me try that again. -2, okay? See? -2. Now, what about the value of the function, of the derivative, sorry? The derivative is 0 here. And so I'm going to draw a little 0 slope tangent line right here. Okay. Now, the value of the derivative function here is about 2. So the slope here is 2. The slope of the tangent line to the original function is 2. So I have something now that looks kind of like this. So remember, these are like little tangents I'm drawing, because that's how we originally plotted a derivative function before. Okay, so as we keep going on, over here we've got m equals 1, right? That's the 1. So, sorry, what did I do here? Yeah, that's a 1. So we've got maybe a 1. Now I don't know where we want to put this. Doesn't really matter for now. Oh, sorry, that's positive 1, isn't it? So I'm going to put this up here. Okay. I have a slope of the tangent line of the original function is 0 here, so I'm going to put a little 0 slope here. And then I've got another 1, I've got another 2, so I've got a 1 and we've got a 2. Okay, so remember what we're doing is we're actually plotting the slopes of the tangent lines to the original curve at this point. So watch what I'm going to do now. I'm going to connect what I've kind of drawn here. I'm going to kind of make a little curve that fits with these tangent lines. You see? Okay, I lost it a little bit at the end there. So again, the tangent lines seem to pretty much fit with this graph. So that's a basic idea of the black function there is the basic idea of what f of x might look like. Because from the derivative graph, these are the slopes that are attached to it, okay? Now, you're like, oh, that's a little bit weird. I'm not sure. Do we have to do that? Well, you have to understand that before we took a graph and we plotted the derivative. Now, what we're going to be doing is thinking about the derivative and trying to determine what the original function was. Okay? So graphically, we're working backwards. What does that look like algebraically? That's the question. Of course, we're going to be working algebraically with stuff. So I want you to think for a second here about some of these. If I just gave you the derivatives of some functions, would you be able to guess or tell me what the original functions were? So I'm going to test your knowledge here a little bit. So if the derivative is 2x, what's the original function, do you think? X squared. Oh, really? Well, if I took the derivative of x squared, it would be 2x to the power of 1. Perfect. That's awesome. Yeah, I like it. What about if I gave you a derivative of 3x squared? What would the original function be, do you think? Okay, I heard x cubed. Just plain old x cubed? Okay. So what I'm noticing here is we seem to be adding to the exponent here. Oh, that makes sense because we subtracted from the exponent to get the derivative, right? That's what we learned with the power rule. So you guys are doing this backwards. Okay, that's awesome. Now, the coefficients right now haven't been too much of a problem, but what are we doing with the coefficients? Do we know? Sorry? Oh, okay, no, I'm talking about what am I doing with these coefficients? How come there's no coefficients there? Any ideas? Okay. Well, think about that. Let's keep going. So if the derivative is 2, you said it, 2x. I like it, 2x. Okay, all right. This could be the toughest one right here because there's two parts of this that you've got to think about. Anybody have any idea what this is? Sorry?
Share your screen.
Oh, yes, hang on. All right, so I can hear you now with these masks on. Wonderful. Okay. So you said ln of 2x minus 1. Okay. Now, why would you say ln? What was it about this that made you think of natural logarithm? The fraction. Okay. So we've got a 2 over 2x minus 1. And you remember from just the previous lessons here that we've just been doing is that the ln of x is 1 over x. I like it. I like it a lot. What about this 2? Where does this 2 come from, though? Okay, the derivative of 2x minus 1. So you're talking about chain rule. Okay, that's going to come from chain rule. Well, let's just see. So if we just have the natural logarithm of 2x minus 1, as was mentioned, we could check that by taking the derivative and see if we get what we get, right? So the ln of 2x minus 1 is 1 over 2x minus 1 times the derivative of 2x minus 1, which is just 2, which I end up with 2 over 2x minus 1. Congratulations. Good job. Yeah. A very safe COVID clap. Yeah, you don't want to clap too hard, you know. You might spray particles from your hand. Careful. All right. Okay, I like it. Very good. That's very good. That was a tough one. I wasn't sure you're gonna handle that one. Okay, what about this one? The derivative is cos x. What is the function? It's very good. Sin x. Awesome. Okay, you ready? What's the derivative, the antiderivative of 0? Sorry? A coefficient? 75? Any number? A constant? Okay. So yeah, you're all right. the actual answer here is, well, it looks like we have taken the derivative of some constant number, right, that had no x in it. So a constant. Oh, okay. Now, I'm going to go back here, and I'm going to wreck your whole life, okay? No, I'm not going to wreck your whole life. But look at this. In light of this right here, what if I said that you were wrong with all of these? What if I said you were wrong? You think I'm lying? So it seemed like I was pretty happy with your answers, right? Well, what if I said you were... Because actually, for this first one, this is the original function. And actually for this one, this was the original function. And actually for this one, it was 17 over 2. And for this one, it was plus root 3. And this one, it was minus 2. So sorry, you guys were actually, you were wrong with all of them. You were saying that, but no one was listening? Oh, were you saying that audibly, like out loud? Or were you just thinking it in your brain? Okay. Okay, so what do we learn here? This is very important. No, we don't learn that you are all wrong and I'm not ruining your life, no. But what we learn here is this, is super important, this whole part. So we actually don't know if there was something added or subtracted to this x term to get us this, because the derivative of a constant is 0, so we don't really know what was outside. It could have been 0, but it could have been any other constant. So guess what? There's something called the most general antiderivative, and we actually have to account for the fact that we don't know if there was an actual constant added or subtracted. So guess what? What you have to do when you find the antiderivative is you have to say, I'm going to go, the antiderivative of 2x is x squared. That was correct. But what you have to do is you have to say plus c at the end of every function now. Because you have to kind of say there could be some other constant that we were unaware of. So this plus c guaranteed is going to trip you up, okay? Guaranteed. This is going to be something you have to remember. When you find the antiderivative, you always have to put plus c at the end, okay? And I'll try and remember to remind you all the time. But why is this true? Let me just show you this graph that's in your textbook, okay? This graph is in your textbook. So page 404, you see this graph. Now watch this very carefully. Watch this very carefully. Let's say the function or the derivative is 2x. Here graphed are 3 possible antiderivatives of 2x, and they are graphed. So we could have x squared, plain old x squared, right here. We could actually have x squared plus 1, which is this up here. We could have x squared minus 4, and so on. Now, why is this possible? Graphically, let me show you. Look at this, the slope of the tangent line right here. You see that? So I don't know what number this would be, who cares, but it's the slope of the tangent line looks like that. If I move straight up, and I go right here, guess what the slope of the tangent line here is? Exactly the same. And if I go straight up from there for this graph, guess what the slope of the tangent line is? It's exactly the same. So you can kind of see that if we move the graph of x squared up and down, the slope of the tangent line that's attached to that graph would be the exact same because we're just moving in a vertical fashion. So graphically, there's a bit of an explanation as to why we don't really know what c is, because if this is the derivative, the expression for the derivative, it works for these 3 graphs and, of course, an infinite number of other graphs of the same form. All right? So that's a little bit of unknown. It's kind of like this, right? How many apples in a seed? Well, you could cut the apple open and count the seeds, but how many seeds? How many seeds in an apple? Is that what I said? Oh, did I say apples in a seed? Shoot. Let's rewind the tape. Okay. Let's try that again. I revealed the punchline. I'm sorry. Listen. That's actually the punchline. How many seeds in an apple? You can cut the apple open and count the seeds. But how many apples in a seed, you don't know, because it's just a seed. You don't know how many apples are going to come from that seed. So when we go one way, yeah, I totally wrecked it. See, that's so good, but I totally wrecked it. I was thinking ahead of myself. Darn it! So the application is that the parallel is this. When we take the derivative, we're like counting the seeds in the apple. When we take the antiderivative, we're guessing how many apples are going to come from that seed. Okay, fine. All right, you guys don't like it? Fine. I think it's fantastic. All right, so you see this plus c? Yeah, you laugh at me. I'm going to be laughing at you when you forget plus c at the end of every antiderivative. Oh. Okay, so plus c, look at this, plus c. You got to remember plus c, plus c, plus c, plus c. Now, another thing, second thing we have to remember, if we have a function f of x, we always have written that little fancy little written f of x, right? Well, the antiderivative of f of x is now capital F of x. This is understood to be the antiderivative. And it's usually the capitalized form. So watch this. If f is a function, its antiderivative is capital F of x. Okay? Function, antiderivative. All right? And watch this. The derivative of f of x is still f prime of x. So it's kind of like 3 generations of functions here. We've got little baby f of x, f prime of x. We've got the dad right here, f of x, and grandpa, capital F of x. See that? That's right. Yeah. Isn't that? That's like seeds in a grandpa apple right there. That makes total sense, doesn't it? I don't know. All my brilliant teacher anecdotes are getting mixed. Thank you. Are you clapping for me? Snapping for me? Okay, so here's the summary of what you guys have been doing, and you didn't even know it. You're all poets, and you didn't even realize that. That's another one of my jokes. Thank you. When I rhyme, like I rhyme all the time. Oh! I'm a poet, and I didn't even realize it.
You don't even know it.
I know it's supposed to be know it. It's funnier when I don't say it right. No? Okay, how many of you have seen Back to the Future? Come on. Back to the Future, the movies? There's the 3 amazing movies. Well, young Biff in Back to the Future 2 always says dumb stuff. Like, why don't you make like a tree and get out of here? And then old Biff comes and he says, it's make like a tree and leave, you idiot. He hits him on the head with his cane. Why don't you get it right? Because old Biff understands that he now knows what it's actually supposed to be, and it's funny. I have to seriously edit this video because I haven't hit pause. Okay.
Keep it all in. Keep it all in.
You want me to keep this in? Yeah. This would be the only video that gets any views. Okay. I need some bloopers. Anything with you guys is a blooper.
Yeah, you should make a compilation.
A compilation? Well, I read Shakespeare yesterday.
Yeah.
Okay. I don't know if you've noticed, but I've had this chart up here for the last 5 minutes. This chart is something I need to talk about right now. So, if the function is 0, the particular antiderivative, now what's the difference between, why particular? Well, guess what? Because none of this has any plus c's on them. Particular is, this is the particular function we're talking about. General antiderivative always has plus c. So the general antiderivative, let's spell general. General antiderivative, you'll see that in your textbook and in questions you're going to get. The general antiderivative always has plus c at the end. So they don't bother with the plus c in this chart because they're talking about the particular antiderivative. Now, those of you continuing on with AP, we're going to study more a little later about initial conditions and finding exact functions. So we're going to find values for c given some other information, but that's a little more in-depth study that we'll do later. So that's later. So that's what the general is, plus c. So if you have 0, that comes from a constant, let's say 1. If you have 1, that comes from x. If you have x to the n, except when n is -1, like in this situation down here, but x to any other power, what we do is, to find the antiderivative, you add 1 to the exponent, and then you divide whatever's in front by that new exponent. Okay, so we did this. You guys figured this out. 2x, right? The antiderivative was x squared. Well, what we do is we add, we have 1 here, and we plus 1 to get 2. And then we divide by 1 plus 1, or divide by 2, to get the 1 here. I know, it's amazing. So you add 1 to the exponent, and whatever that exponent becomes, you divide by. So it's just the opposite of power rule, right? And we'll do some more examples down here. We're going to do some more examples down here. So, but just write some of this down here. So 1 over x, the antiderivative, ln of absolute value of x. Okay, 1 over x is ln of x. E, okay, E is a good one. And again, remember how easy E was to take the derivative of? Well, thankfully, taking the antiderivative of E function is almost as easy. So e to the x, of course, is e to the x. But e to the kx, let's say we have, for example, e to the 2x. Well, it's e to the 2x, but we have to do 1 over 2. Okay, so e to the kx is 1 over k, e to the kx. That's the antiderivative. Because if we took the derivative of this, it would be 1/2 e to the 2x times the derivative of 2x. See? And then sine and cos. So if you have cos of whatever constant times x, as long as k isn't 0, but cos of 2 or 0.5 or -5 or whatever, okay, obviously the antiderivative of cos is sine, and then you have to do 1 over k. So to account for the chain rule. So this is undoing the chain rule. That's why we have to do this 1 over k, 1 over k, 1 over k. We're undoing the chain rule. Okay. So sine of kx, now the antiderivative of sine is negative cos. So I know you just learned what the derivative of sine and cos was. Well, now we got to learn that when we do the antiderivative, it's kind of opposite. Okay, cos still goes to sine, but the negatives are different now. You'll get used to it. You'll get used to it. What I do still is when I do the antiderivative, sometimes I just quickly look at the antiderivative that I wrote, and I just take the derivative in my head and see if it works, just quickly before I move on. It's like, okay, derivative of that would be, yeah, we're good. So work through it in your head. Take your time. It's going to take some time. But let's do some examples. These are from your textbook as well as some homework questions I'm going to do with you now. All right? Okay, so antiderivative of a here. We're going to take each term separately. I'll zoom in here so you can see. We're going to take each term separately and find the antiderivative of each term. We're just going to simply add them all up. So for a, capital F of x equals, this is going to be x to the 3. I add 1. And then I have to divide whatever's in front of x by 3, because that's the number that I just put there. Okay? So you add 1. So this is x to the 1. So let's make that x squared. And I have to divide by the number that I just put there. Because, I mean, when we're done here, I'll show you, because this is 7x, right? Now, antiderivative of f, this is the particular antiderivative, but we're going to practice putting plus c, some constant, unknown constant that could have been there. We're going to practice doing that. Okay, and I'm going to forget sometimes too. I'll try not to, but plus c. Now, if I take the derivative of this grandpa function here, right, to get regular old f of x now, I take the derivative of this. 3 comes down, multiplies by 2/3. 3 times 2/3, x to the 2. What does that equal? Well, that equals 2x squared. Is that what I started with? Yeah. Okay, what about this one? Oh, the 2 comes down to multiply by 1/2, and I subtract 1 from the x. Boy, let's see, that's just plain old x, right? That's what I started with. And of course, the derivative of 7x is plus 7, and boom. That's what I started with. See that? Okay. All right, so you guys are focusing well here. This is good. Just lots of practice we need. So b, over here, let's do b. So capital F of x, right? What's the antiderivative of cos? We just had it in our chart here. The antiderivative of cos is positive sine. So it's simply sine x. Minus, what's the antiderivative of sine? Negative cos. Yeah. So sine x plus cos x plus c. All right. Speaking of c, here's c. Capital F of x, which means the antiderivative of this. Okay. Ooh, this looks tough. Well, the antiderivative of e to the negative x is simply e to the negative x. I know that. That's what's great about e to the x. But I have to account for the power rule. So whatever this number is, in taking the derivative, I would multiply by this. So now, going backwards, I have to divide. Divide by -1. And we'll simplify in a second. Plus, okay, ooh. Remember, e to the 2x, the antiderivative of e to the 2x is e to the 2x. But I have to divide by 2. Whatever's out in front, or I multiply by 1/2, whatever. See that? So this becomes, I'll just simplify here right beside. Obviously this is plus 3 e to the negative x. And this is plus 3 e to the 2x plus c. Take the derivative of this. Well, it's 3 e to the negative x times -1. Yes. Got it. E to the 2x times 3 times 2. Yes. 6 e to the 2x. Okay? All right. On a scale of 0 to 5, 0 means I have no idea what you're talking about. You're speaking Romanian to me.
Oh, I can understand.
Yeah, you can understand that, right? Okay. But that means you have no idea what I'm doing right here, and you're totally lost. And 5 means, Mr. Maxwell, I could do this in my sleep. I could actually come up there and teach for you, and I would like to come up there and teach the rest of the lesson for you. So what is it? Where are we at between 0 and 5? Anybody speaking Romanian? No? Anybody want to come teach? Hey, the Romanian wants to come. Okay. Yeah. Yeah. Okay, well, here's my notes. I actually made notes for this lesson. Here you go. Come on. Okay. Yeah, messed his pants just a little bit there.
I think Daniel gets it. You should be.
Yeah. Okay. All right. Yeah. Yeah. I do have notes, but no, I'm not going to give them to you. How about I continue teaching? Okay, real good. Okay. All right. Let's do some more practice. A. Capital F of x equals. Boy, I need to make this to the power of 1. I need to make that a squared. And I need to divide by the 2 that I just put up as the new exponent. And this 1 must have come from a 1x. So I've got x squared plus x. Does that make sense? If I take the derivative of this answer here, do I get my original function? Let's see, 2x plus 1. Yeah, that should be it. Okay, there's your answer for A. Oh, plus C, plus C, plus C, plus C. Don't forget. Most general antiderivative, plus C, plus C. All right, capital F of x equals. Oh, I need to add 1 to this exponent. I always do that first, and then I know what I need to divide by. You see? So 4 over 4, x to the 4th. minus 11x plus c. Simplified is x to the fourth minus 11x plus c. Taking the derivative of this, that's 4 comes down, x cubed, 4x cubed, yep, minus 11, minus 11, awesome. And then if this was some constant like 2, what's the derivative of 2? 0, good, I've got a plus 0 there, perfect. Right? Okay. I tell you what, why don't you do C right now? Do C on your own and see if you can get it. And I'll show you, actually do C and D. Take a minute or two and do C and D, or write it down. And then I'll show you what I got up here and we'll see if they're the same. These are the answers you got. So for C, I've got capital F of x equals simplified 8 over 5 x to the 10 minus 9 over 5 x to the 5 plus 3 over 2 x squared plus c. And then over here, we add 1 and divide by that number. So we got 1/8 x to the 8th plus this, and so on. Okay? Plus c at the end of all of those, correct? Yes. Okay? All right, let's keep going. These ones look really nasty, but they're not. What I would suggest here is that you rewrite this before you take the antiderivative. You know what? Let's make these in the denominator here. Let's make them negative exponents. And this is actually just 1/2 or whatever, right? X to the 5th. So you might want, I don't know if you want to do this or not, but this negative one probably is a good idea, okay? Because then we can use this sort of anti-power rule, right? So capital F of x now, I'm going to add 1 to the exponent. That's still the rule, whether it's negative or whatever, as long as it's not -1, right? So add 1, and I'm going to divide by that. Okay, so add 1 gets me to x negative 6, so I need to divide by -6. So this is going to be x to the 6th, and I need to divide my coefficient by 6, or write this as 2 times 6 down here, right? So 1/2 divided by 6 would be 1 over 6 over 1, or 1 times 1 over 6. So this is -1/3. Now if you want to write this with positive exponents, I will in a second. That's a good idea. That's considered simplified if you have positive exponents. So I'm going to go -1 over 3x to the 6 plus 1 over 12. I guess that 1 is, we'll make that a x to the 6. X to the 6 over 12. Something like that. And I'm fine if you just stop there. Yeah, we could pull out a 1/3 and all this sort of stuff, but we won't. Okay, so the main business here is this kind of first big step, right? You need to know how to do that. Okay, I'm going to move me over there. Let's take a look at this question for B. Any questions about A? So for B, capital F of x. Maybe x to the positive 1/2 might be better, and x to the 1/3 might be even better yet. The square roots, the cube roots, you write them as fractional exponents might be a little easier. So this is going to be x. Okay, now I have to add 1 to this. So 1/2 plus 1 is actually 3 over 2, right? And I have to divide here the coefficient by 3 over 2, which is the same as multiplying by 2 over 3. So if you have to divide by a fraction, flip and multiply. That's pretty much what I did here, right? I multiplied by 1 over 6. So if you have to divide by a fraction, flip and multiply. Plus c. Yeah, see, I remembered. Just a little late. So x to the 1/3. Oh man, see, it's tough, eh? So x to the 1/3, add 1. That's x to the 4/3, and then divide by 4/3, so it's 3/4 plus c. Can we skip this unit? Let's see. The short answer is the antiderivative of yes. Boom. Gotcha. Okay. What is the antiderivative of yes, anyways? No. It's no. No. Okay? The gift of no. Any questions other than can we skip this? Any other real questions that can contribute to the class here at all? No? You guys got this cased? Nice. Let's do something harder. Oh. Home time. Not quite. All right. Not quite. Still got a few minutes. Okay. I have no idea how much. I have lots of examples left. So let's get through this quick in the next few minutes here. The bell might ring before I'm done, but that's it. You're going to stay. Okay. Capital F of x. Let's get through this. Here we go. Sine of 2x. Oh, that's going to be what? The antiderivative of sine is cos? Negative cos. Thank you. Negative cos 2x. Oh, but what do I have to do? I have to undo the chain rule. So I have to do 1 over 2. Hey, what do you think? Plus 2. The antiderivative of cos is sine. No chain rule to undo here, so I just leave it like that. Plus c. Plus c. Plus a. Plus a. Okay, moving on. Haven't got much time. Antiderivative. Oh, some whimpers. What's the antiderivative of e to the x? Correct. E to the x. What's the antiderivative of e to the negative x? Correct. E to the negative x. Times, or divided by, negative 1. E to the x minus e to the negative x. Plus c. Boy, this class is devolving into something chaotic here. Come on. All right. Okay, one more. One more. Let's go. One more. Sit down, Jack. That's right, Jack. I'm the boss. The bell is not the boss, Jack. If you haven't figured that out yet. The boss is right here. Okay. It's all your fault. If you guys wouldn't have distracted me, all that goofing around earlier. Okay. Let's do this one. Now, I should probably make you guys do this one. No, I'll help you. So we've got a little bit of a product rule here. Now, think about this. The antiderivative of e to the x squared is e to the x squared. I would normally have to multiply this by 2x if I was taking the derivative. So I actually have an x here. So how would I undo the chain rule? How do we undo the chain rule? We kind of, instead of multiplying by the derivative of the inside, we kind of divide by the derivative of the inside. So guess what? You put a 1/2 there to undo the 2x that you would have normally multiplied by. And that's it. Now, there's a couple more. I'd like you to try this one on your own. And of course, we do have a homework assignment that I'll let you work on tonight. But the bell has rang. Thank you for letting me know that, Jack. And
Thanks for letting us do that.
thanks for letting you stay. Thank you. You're welcome. You're welcome.
No,
All right. Any final questions before I hang up here? Yep.
Can I take this? I'm gonna skip this.
Can you what? I can't hear you. Are you speaking Romanian again? Still didn't hear you. No, you want to teach this class? Okay, maybe next time.
It's good.
Yeah. Okay. Whatever. See ya. Okay, you're dismissed. Get out of here.
Wait, what's the assignment?
Go log on to the website. Hey, I'm almost at 1,000 subscribers. You guys aren't working hard enough. Let's go. Tell your friends. Let's go.